Okay, yeah, we finished the finding of roots of equations. I mean, there we looked, yeah, let's do it in the reverse order. We finished with the Newton's method. We did fixed point iteration, interval bisection. Yeah, that's the three methods we looked at. So, yeah, I mean, this is now, or was the end of this first numerics chapter. And now we go into function approximation, which also, at least by part, is numerics, because we will use numerical algorithms for this. Okay, so let's start right ahead. We start with polynomial interpolation. No, let's go one step back. So what is function approximation? I mean, in this chapter, our task will be, given a set of data points, we want to have a function that, yeah, I don't know, interpolates, approximates, or maybe hits all the points. So the task looks like that, one-dimensional, given a couple of points, maybe like that. And now we want a function through all these points. Oh, the function didn't hit this point. Now, is this a fault, or should it be like that? I mean, that's the type of questions we will ask. Huh? But, I mean, before we talk about algorithms that solve such a task, we have to define the task. Huh? If the task is not well defined, then there are typically infinitely many solutions. For example, here, if I just give you the points and say, fit a function through these points, then what does that mean? Is this okay, or is this a fault? A fault? You would say a fault. I would say it's okay because this is an outlier. Or what would you do if the points look like that? I mean, one solution is like that. Is that what you expected? Yes? You would like this. Huh? Who doesn't like that? What would you have? A straight line. Like that. Yeah, that looks better, doesn't it? But I mean, yeah, it's a matter of taste, is it? That's nice. Now mathematics is a matter of taste. I mean, he likes that, the other guy likes this. And maybe someone else would say, oh no, not a straight line. Why don't we use a logarithm? Infinitely many solutions. They're all nice, aren't they? Yeah, so maybe mathematics is not so far from psychology. Huh? I mean, what you should learn from this is, first we have to define the task. Huh? Let's look at this picture again. So now here we have a number of data points, and there we have a function that hits all the data points. So maybe we clearly specify that we are given a set of points, and we are looking for a function that hits all the points. And now the task is well defined. Okay? No! Still infinitely many solutions. This is also a solution. And maybe like that. Of course, we have to, I mean, this is a function. It's a stepwise, a piecewise constant function. It is a function that hits all the points. And of course, given a set of points, you almost always can find such a function that hits all the points. You see, the problem is not yet well defined. There are infinitely many solutions. Or, I mean, this one would also be a solution. This is also a solution. It's perfect. Maybe you are not happy about this blue curve. Who is not happy about the blue curve? You're all happy with this? So we are finished. You're still happy? You're afraid of my questions when you say you're unhappy, I know. Why are we unhappy, for example, about this? Because this is, I mean, in machine learning we would call this overfitting. We fit something which is not there. Huh? The complexity of this function is by far too high. And why are you unhappy about the green function? It's not continuous, thank you. Yes. So, okay, so you see, maybe our next requirement should be we want to have a continuous function that hits all the points. But still, if you say continuous, the blue curve is continuous. It's perfectly continuous. Huh?
But not monotonic? Not monotonic?
It's not monotonic. Would you expect a monotonic function through these points? No. But it might be a requirement. So if you're happy about monotonic functions all the time, but then there is no solution here. Okay, so you see there is a narrow line between infinitely many solutions and no solution. So if your requirement is monotonic and hit all the points, there is no solution. Yeah. Okay, and we will look at a couple of different tasks. Our first task is, given a set of points, we are looking for a function that hits all the points. And we already discussed this is underspecified. We need more requirements, yeah? Because we don't want to have this effect. And what we do in the first step is something very simple. Function has to hit all the points, and second, the function has to be a polynomial. So we already clearly specify the class of functions that are allowed. Okay? But this is still underspecified. Why? Now, I mean, you know from, I don't know, maybe your bachelor's, maybe from school, given 2 points, you can uniquely determine what type of function through 2 points.
The linear function.
Yeah, yeah. A straight line, which is a fine linear function. Huh? Okay, so, and this is a polynomial of degree 1. So we have 2 points, and then we uniquely can determine a polynomial of degree 1. Now, what is it if our polynomial has degree 2? Is there a unique polynomial of degree 2 given 2 points? No, there are infinitely many, of course. I mean, here there would be this parabola, or maybe this, or this, and so on. Infinitely many solutions. How many points do we need for a parabola? 3 points. And for a cubic polynomial, 4 points. Okay. So you see, we always need one more point than the degree of the polynomial is. Huh? Or in other words, if we are given n points, then there is a unique polynomial of degree n minus 1. Okay, and that's polynomial interpolation. Yeah. Oh, Zeigestück. Given such a table of points xk, yk, and we are given n points. Sort is a polynomial p of with the property p of xi is equal to yi, and that means, what does that mean intuitively? The polynomial hits all the points. Okay, and now this is our ansatz. And you see, given n points, we require the degree of the polynomial to be n minus 1. For the obvious reason we have just seen. Okay, so now this is our polynomial. And you all know how you determine these coefficients now. How would you do that? I give you 4 points and you have to determine the coefficients of a cubic polynomial. How would you do that? Given 4 points, sort are the coefficients of our cubic polynomial. What would you do?
We have these 4 unknowns, and with these 4 points we can make 4 equations.
Yes. Yes. So we substitute the 4 points into the polynomial equation and get 4 equations for 4 unknowns. And what's really nice is that these 4 equations are linear equations. So then you have a linear system with 4 equations for 4 unknowns. So then you look into the strength topics and you know how to solve it. And hopefully you also know whether to solve it or not, because not all linear systems do have solutions. Huh? Okay, yeah, I mean that's what we do here on this slide. Look, we substitute our point number I, xi, one of these points, into the polynomial, and on the right hand side we get yi. Why do we get this? Because of this requirement. P of xi is equal to yi. That's what we require. Huh? Okay, so we get this equation, but this is not one equation. This is a set of n equations. So this must hold for I equal 1 to n. Yeah? So we get n such equations. And look, in the first equation, it starts with a1 plus a2 times x1 plus a3 times x1 squared, and so on, up to x1 power n minus 1. Okay, and we can write this linear system in matrix form. Here we have this matrix capital A times the vector of our unknown variables. And the unknown variables are a1 through an. And what is this matrix A? Yeah, this matrix A contains all the rest we have here, which is 1 times a1 plus x1 times a2. Look, 1 plus x1 plus x1 squared, and so on, up to x1 power n minus 1. And in the second line, the same with x2 and up to xn in the last line. And this is the so-called Van der Monde matrix. And this matrix, be careful, this matrix does not contain variables x1 through xn. No, it contains numbers. This is just a numeric matrix full of numbers. Why? look, these xi here are not variables. They are the data points that are given. Okay? So given our data points, what you have to do is you fill up this Vandermonde matrix and you fill up this vector of the right-hand side with these yi's, and now you have this linear system. And the task is to solve this linear system for this vector A. I mean, that's a really simple thing. Huh? Okay, and now of course the question is, does this linear system have a unique solution? And the answer is here. If the x components of our data points are all distinct, that means if not two xi are identical, like take these points. I mean, if this is x1, and if there is a second point like that, it has the same x value, and that's not really nice, because it's not possible to find a function through these 2 points. So it's really obvious that we have to require the xi have to be distinct. Then for any vector y1 through yn, there is a unique polynomial p of degree less than or equal to n minus 1 with p of xi equal yi. I mean, this is our requirement, that it has to hit all the points. What's maybe interesting is that the polynomial p is of degree less than or equal to n minus 1. So that means, for example, given 3 points, it may be possible that our polynomial has degree 2, 1, or 0. Who can give me an example of 3 points where the solution is a polynomial of degree 0? A circle? No, a circle is not a polynomial. No.
All points are the same.
No, that's not allowed. The xi have to be distinct. What is a polynomial of degree 0? Yeah?
If all points have the same y value.
Yeah. Yeah. So they are kind of constant. So the picture looks like that. And then the solution is a constant function. That's a polynomial of degree 0. Okay. Or, I mean, in other words, of course you could say it is a polynomial of degree 3, but it is one where the 2 leading coefficients are 0. But, I mean, let's talk about the definition of a polynomial of degree n. The degree of a polynomial is the highest order coefficient which is non-zero. And therefore, this is a polynomial of degree 0 and not of degree 3. Okay, and now let's look at the proof of this theorem. Yeah, we want to show that this linear system, this matrix A times the vector A is equal to the vector Y, that this system is uniquely solvable. That this has a unique solution. And what we do now is we show that the null space of this matrix A is the 0 vector. And this is equivalent to the system has a unique solution. So if because the null space would be bigger than just the 0, then the system wouldn't have full rank, and then it wouldn't have a unique solution. Okay. So we have to show that this system, matrix A times vector A equal the 0 vector, has the only solution A equals 0. Because this is the null space is the 0 vector. Okay, so now we look at this system equals 0. What does that mean? I mean, this matrix A comes from substituting all the points into our polynomial. So this is equivalent to, for all the points, P of xi is equal to 0. Or, I mean, you could see it differently. This 0 here is the replacement for this y vector. And the y vector are the values of our points. So now we have a couple of points just on the x-axis. Okay, now look at this. So for n points, we have P of xi is equal to 0. P of x1 is 0, P of x2 is 0, up to P of xn is 0. And our polynomial has degree n minus 1. Now let's look at an example. Given 3 points, and they all have to be on the x-axis. Oh, should we switch on the light? At least this one. You need more light? You can have, of course. Okay. 3 points on the x-axis. Sought is a polynomial of degree 2. A parabola. Have you ever seen a parabola with 3 roots? That's kind of funny, isn't it? I mean, I could imagine a parabola like that. Or maybe like that. But not something like this. Huh. The only polynomial that hits all these 3 points is this one, the 0 polynomial. So that means, so if we require this and the degree of our polynomial is less than or equal to n minus 1, then the only solution is the 0 polynomial. Okay. So our polynomial is equal to 0, and what does that mean? That means all the coefficients are 0. And now our vector A is 0, and that means the null space is the 0 vector, and therefore there is a unique solution. Where did we use the fact that all the xi are distinct in this proof? Where did we use this fact?
For all values of I equal to 1 to n, pxi equal to 0.
Yes. If here we allow 2 points to be the same, then we no longer have 3 points here, but only 2. And then, of course, there is a non-trivial parabola which hits the 2 points. So at this point, we really need the fact that all the points are distinct. All the x values are distinct. Okay, yeah, that's it. I mean, now we know everything. We know how to find our polynomial, and we know that it works if the x values are distinct. Let's apply it. Here we have an application. So what I did is I want to try whether this new method works. And in order to try whether something works, it's good to have a problem where I already know the solution. And now I took the sine function, which is this dashed line. This dashed line is the sine. And now I took 5 sample points from the sine, which are these points. And for 5 points, I can interpolate a polynomial of at most degree 4. And this is our polynomial. This is what we get. Isn't it nice? In this interval between -2 and +2, it's quite a good approximation of the sine function. And if we take more points, we get an even better approximation. So now we took points between -3 and +3, 7 points. And I mean, here we get quite a good approximation. Of course, outside the interval, we cannot fix the polynomial. Of course, I mean, we know that a polynomial goes to infinity for x towards infinity. So it cannot be like a sine towards infinity, and to minus infinity the same. But it looks quite nice. We can take even more points. And we get a very nice approximation of the sine function. Yeah. But now let me show you that it's not that nice all the time. This is the classical counterexample. We take this function, 1/1 plus 25x squared. And this function looks quite similar to such a Gaussian normal distribution. Yeah. I mean, to me, this function would look even simpler, much simpler than such a sine. I mean, the sine has infinitely many oscillations. This function only has one little hill in the middle, and here it's kind of boring. Yeah? But it's obviously not well suited for fitting a polynomial. I took even 2, 4, 5, 11 points. We took 11 points, which is well, not such a small number. I mean, taking many points means there are many points where we fix, where we clamp our polynomial. I mean, the polynomial has to meet this point and this point and this point. But I mean, the approximation is fairly well here in the middle. Not really good, but maybe acceptable. But already here, we get such a not nice oscillation, and here, and it's getting worse and worse. Yeah. Oh, I forgot to bring the tool. I have a nice tool that a student programmed for me, where I can, with the mouse, take such a point and move it around, and I can insert additional points in between. Okay, I don't have the tool here. Let me ask you, what would happen? I mean, isn't it an obvious idea to add an extra point here? Of course, I mean, we would really force this oscillation to get down here. But that would not solve the problem. the problem would get worse. It would get even worse. I show you what would happen. So if we would, suppose we would add another point here, and one here, and one here, and one here, and here the same. Of course we would force this guy to get up here. But I mean, this is like if you have a Hiwi. You know what's a Hiwi? A Hiwi is a student who works for me. Huh? And if I don't specify the task well for the Hiwi might escape like this polynomial here. Huh? I mean, the only thing I specified here was hit this point and hit that point. And now, I mean, this is not a nice Hiwi here, because he tries to escape as far as he can in between the points. Huh? And I mean, if it's a not nice Hiwi, and I specify these extra points, what would this guy do? I mean, he would, of course, do something like that and go down even further, and something like that would happen. And it would really happen, especially here in the outer part of the polynomial. And you understand why this happens. I would add 10 extra points here in order to clamp the polynomial down to our function. But why is this a bad Hiwi, this polynomial? Now, what do we know about the relation between the number of points and our polynomial?
We get a higher degree polynomial.
Yes.
The function's only of degree 2.
What would the degree be then? We have now 21 points.
20.
The degree would be 20. What does it mean, a degree of 20 for the polynomial?
There are many solutions.
Many? No, not many. One unique solution.
That many roots.
How many?
20.
20. Yeah, I mean, we get 20 oscillations around here. But my question is, why are these new oscillations much worse than the old ones?
We have got the roots in the same interval like before.
Yeah, that doesn't answer my question. No, the answer is really simple. The highest order term of the polynomial then is x power 20. Can you imagine that x power 20 goes to infinity faster than x power 11? Much faster. By a factor of x power 9 faster. Obviously, the slope here at the margin of the interval is much higher than it was before. So it's not a good idea to add extra points for our polynomial. Because with every new point, I increase the degree of the polynomial. And the polynomial has to go to infinity very steeply. That's the problem we have. And that's why we are not finished with function approximation. Huh? I mean, yeah, it would be nice if we could solve everything with polynomials. Huh? But there are some properties which are not nice, as you can see here. Yeah, now, it's not a good idea to add extra points. But I mean, I already told you what's the solution when I mentioned this software tool the student built for me. In this tool, we can move points around. And that's a much better idea, because moving points around does not increase the degree of the polynomial. Huh? Look, the error that our approximation polynomial produces is it's exactly so high here. This is the error of this polynomial. And of course, we want to decrease this error maybe like that. How can we decrease this error? We move this point along in this direction. And maybe this one also a little bit outside. And then what happens is, let me show you this. Here, the number of points is still 11. But what we did is, we moved the points towards the margin. This one out, I mean this point, I guess it was here. And this one was here. So we moved these points towards the margin. And in the middle, the distance between the points is bigger, as you can see now. And I mean, I could give you this tool, or you program it by yourself, and then you can play around. And there are infinitely many possibilities to position 11 points on an interval -1, 1. So you can play around infinitely long until you find this optimal solution. And maybe it's better to do a little bit mathematics and to know the formula. I mean, there was this ingenious mathematician, a Russian mathematician called Chebyshev. He found a formula how to position our 11 points on this interval such that the maximum error, which is this here and this, you see, the error here is about the same as it's here and here and here and here. So the points are distributed in a way such that the maximum error that our polynomial produces is minimal. That's the task. Okay, now let's go back to this question. Yeah. So we have to talk about the maximum error of our interpolation polynomial. That's why we here define the maximum norm on functions. What is the maximum norm of a function? It is the maximum over all x in a given interval of the absolute value of our function. Yeah. And now, excuse me, yeah. Yeah, so now once we have defined this maximum norm, we can talk about the difference f of x minus p of x. F is the given function, p is the approximation polynomial, and now this is the difference between these two, and then we take the absolute value of the difference between these two, and we consider the maximum of this absolute difference on our given interval. So the maximum for x in AB, and this is nothing but the maximum norm of f minus p. And our goal is to find a polynomial such that the maximum norm of f minus p is minimal. That's our goal. Okay. Yeah. Yeah. And now a theorem that Chebyshev used to prove his theorem, where he says how to distribute the points, is this one. Look, it talks about the difference between f and p. This is our relevant measure we have to minimize. Okay, now, and the requirements are f has to be n times continuously differentiable. And then we have this interval AB, and on this interval we have our data points x1, x2 up to xn plus 1. And they have to be distinct, of course, and they have to be ordered. So x1 smaller than x2 and so on. And p is our interpolation polynomial of degree n, with p of xi is equal to f of xi. Yeah. Now this is a little bit different to what we had before. Before it was p of xi is equal to yi, our given data points. But now we have a different task. Look, we switched the task. Now we are talking about the task given a function, thought is a polynomial that approximates the function. So that's a new task. It's a different task. Okay. And that's why here we require p of xi is equal to f of xi. Okay, so the new task is, go back to the picture. Given a function, the dashed line, and a number of points xi, x1, x2, x3, and we want to have a polynomial of degree n that hits the function at all these points. Okay. And then there is this nice formula for our approximation error. And now look at the right-hand side here. Isn't that nice? That reminds you of what? Finding similarities between formulas is very important in mathematics. Remainder term? Of what? Of the Taylor series, yes. Thank you. Yeah. I mean, in the remainder term of the Taylor series, you have an n plus first derivative of a function. You have n plus 1 factorial in the denominator. And here it's different. So what would we have in the remainder term of the Taylor series here? So just one person who wants to say something.
X minus x naught.
X minus x naught power n. Yeah? Or here it would be power n plus 1. Yeah. Yeah. Yeah, that's what we have. So we would have here, so we could kind of delete all this and here put the power n plus 1. Okay? But this is quite similar. How about replacing the two? Oh, sorry. How about replacing the 2 by a 1 and all these indices just by 1? And then it's x minus x1 power n. Yeah. That's quite nice. So now, but x1, 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 this is actually forbidden. Why is it forbidden?
It's not distinct.
Yeah, the points are not distinct. But let's do for a moment something forbidden. Yeah? So we put all points together to one point. I mean, that's what we did in Taylor expansion. In a Taylor expansion, we want to approximate a function by a polynomial in one point. In one point only. But, I mean, there are infinitely many solutions. There is only this one requirement. This gives us one equation for n unknowns. How does this work in Taylor? We forgot n minus 1 requirements. What are the other requirements? The first requirement is the Taylor polynomial has to hit this point. And what is the second?
Derivatives.
Yeah, the first derivative has to be exactly the tangent, and the second derivative and the third and so on. So we have n requirements from n derivatives. And so we get n equations, and that's how we compute the Taylor formula. Okay, here we have n different requirements. Here we have n zeroth order Taylor requirements. We have to hit this point, and this point, and this point, and this point. And that's why we get this product of x minus x1, x minus x2, and so on. So that's, yeah, I mean, it's really nice to compare this with the Taylor expansion. Okay, yeah. Yeah, okay, and the question that Chebyshev asked himself was, how should the given points be distributed to minimize the maximum error? And now he took this formula and started to minimize this error term. And we don't look at the proof, we just look at the result. And this is a really nice result. We are talking about the interval from -1 to 1. Look, we are just talking about this example between -1 and 1. We will generalize this later to arbitrary intervals. Oh no, one more. Okay, f defined on this interval, and p is our interpolation polynomial at the given points on the interval between -1 and 1. So we have n points in this interval. And of course, we don't know where these points have to be. But this theorem tells us. The approximation error is minimal if we distribute our xk like minus the cosine 2k minus 1 over n times pi half for k equal 1 to n. And these values xk are called the Chebyshev abscissas. Yeah, and now let's look at an example. For n equals 6, these are the points between -1 and +1. And you can clearly see that the distance here is about half the distance here in the middle. And yeah, what happens if we apply this is this. You have seen it already. Okay, so what we learned is that Chebyshev, I mean, this is then called Chebyshev interpolation. We have learned that Chebyshev interpolation reduces the maximum error. And the result is this. The good news is it's much better than what we had before without Chebyshev. The bad news is we are still not satisfied with this. And that's why we have to continue and look at other methods. And this is actually the best we can do with polynomials. We can't do better. Look, I mean, this is an optimality theorem. The approximation error is minimal if you distribute your n points like this. You can't do better with n points like this. What you can try is increase the number of points, but I'm afraid it would be worse. It wouldn't be better, it would be worse. Or you can decrease the number of points. And that would actually be a good idea. In this example, it would be a good idea. Not always, but in this example. Why would it be a good idea here to reduce the number of points? And let me ask the second question. How many points would you use to get a better approximation?
3 to 5.
3 to 5? Yeah, that's a good idea. 3 points. Let's talk about 3 points. You would take this point, and then maybe this, and this. How about that? And then you would get a polynomial of degree 4, which would look, I don't know exactly, like that. Polynomial of degree 4 looks like such a W, something like that. Huh? I mean, that would be much better an approximation as this, and it would also be better than this. Yeah? Maybe go back to this picture. Yeah, and maybe 5 points might also be a good idea. So you would use this point, and maybe this, and this, and this. That's a good question. We should actually try it. Nobody knows what would happen. I'm afraid the picture would look like that. Something like that. Huh? Yeah, but then, what can we do to improve it? Distribute it like Chebyshev told us. Yeah? And that would mean we have to move this point around here. And then it might be quite good. Okay. Yeah, so much about polynomial interpolation. Oh yes, I promised you to give you a formula for arbitrary intervals. Here we only talk about -1, 1. Okay? And here is the formula for arbitrary intervals. That's the formula. Ja?
Beim ersten Bild, was Sie gemacht haben, haben Sie 3 Punkte genommen und dann eine...
Hier?
Ja.
Nö, das mit dem Sinus.
Nein, weiter. Schon bei dem Bild.
Ja?
Da hatten Sie doch 3 Punkte genommen und dann ein Polynom des Grades hoch 4 genommen. Wie geht das?
Ach so.
Das kann ja eigentlich nur eine Parabel.
Oh ja, stimmt. Sorry. Ja. Thank you. So he is perfectly right. I'm sorry for that. Yeah. Thank you for this hint. So what I did is I took 3 points, and then a polynomial of degree 4, which is nonsense. Yeah? So what the solution here would be something like that. Of course, we would get a parabola. Thank you. Yeah? So we have to take 5 points in order to get a polynomial of degree 4. Which then, now let's do it again. 5 points like that, and we get a polynomial of degree 4, which is such a W kind of shape. Yeah, it may look like that, but it may also look like that. We don't know. Yeah? Yeah, so we have to take 5 points, and then maybe we get a kind of reasonable result. Okay, so where have we been? Ah, yeah, here. This little corollary tells us how to distribute our points if the interval is an arbitrary interval between A and B. And of course, it should work for arbitrary intervals too. And what to do? A 2-step procedure. Step 1, you just calculate the ordinary Chebyshev abscissa, which are between -1 and 1. And then, these are the xk here. And then you take all the xk, apply this formula, and get the new tk, which are now the points in this interval. Yeah. So you first compute the Chebyshev abscissa, then apply this formula, and that's it. And then you use the TK as your x points. And it is very easy to prove this. You can do it at home. It's a nice exercise. How can you prove this? I mean, this formula is nothing but a linear mapping of the interval -1, 1 onto the interval AB. That's it. So you look at this picture. We want to map this interval onto an arbitrary interval AB. Now take the y-axis, and here we have A, and here we have B. And that means we want to map -1 onto A, which gives us this point, and 1 onto B, which gives us this point. And this straight line here is the formula over there. And you all know how to fit a straight line through 2 points. That's it. Okay, yeah. Now we are finished with polynomial approximation. We see that it's very easy, but that it's limited. Now what can we do to solve the problems? Let's go back to the picture here. Or no, let's go back to the other picture. It's even better. I mean, here the only solution is to use the Chebyshev abscissa. What's not a good idea is to add extra points. Maybe it's a good idea to decrease the number of points, to use fewer points. And also, I mean, you see the problem here comes from the high degree of the polynomial. And the high degree of the polynomial produces high oscillations near the margin of the interval. Because for large values of x, our polynomial has to diverge. It goes to infinity. So maybe it would be nice to have a degree 3 polynomial here and here, everywhere. Huh? But if it's only degree 3, then maybe it's not powerful enough to represent arbitrary shapes of the function. But that's the next solution we will look at. And it's called splines, cubic splines. Cubic splines is a method where we do the following thing. We take a number of points, and the function may be very complex. And what we now do is we approximate a cubic polynomial between these 2 points and another polynomial here in between, and again another polynomial here, and another cubic polynomial here. Oh no, that doesn't look like this, and so on. The big advantage of this is we have a small degree, which is only 3 everywhere. Only polynomials of degree 3. So that means we don't get such bad oscillations anymore. Of course, the disadvantage is we have many polynomials. This is number 1, 2, 3, 4, 5, 6. Yeah. Piecewise polynomial approximation. That's what we do next. Okay, yeah. And also, we already mentioned, it's a good idea to reduce the degree of the polynomial. Yeah? I mean, this reduces the number of parameters. Yeah. And there are in German it's called Faustformel. What is Faustformel in English? Who knows that? Oh, rule of thumb. Yeah, it's a rule of thumb. There are such rules of thumb, and one rule is the degree of the polynomial should be less than or equal to 2 times square root of n. So if we have 100 points, then the degree should be 2 times 10, which is 20. But, I mean, you can more or less forget this. Maybe sometimes it works, but normally it wouldn't work. Yes. Yeah. But how about, suppose you do that. You have 100 points, and you take a polynomial of degree 20. That's impossible. Why is it impossible? Because we have proven, given 100 points, there is a unique solution of degree 99. And how about degree 20? You get, from these 100 data points, you get 100 equations for 20 unknowns. That's what we call an overdetermined system. And this will be our third next approach. We will then look at overdetermined systems, and this is very interesting. Yeah? Solving overdetermined systems exactly for such function approximation tasks is a very powerful solution. Yeah? Not only for polynomials, even for other basis functions. So this will be a next approach, a very interesting approach. Okay, yes. Yeah, I will omit this. I just mentioned this. Who has never heard about the Horner scheme? Oh, these are too many. Okay, so you read it somewhere in Wikipedia, wherever. And you need to know it, because it's a nice little trick to evaluate polynomials efficiently. Oh, maybe I say a few words. Okay. This is our polynomial. Now, when you do it in MATLAB on the computer, maybe drawing such a polynomial, for every point you draw, how many numeric evaluations has the computer to do? I mean, there are about n additions, and how many multiplications? There are n multiplications, but then there are these exponential operations which are very expensive. Yeah? If you do it naively, then here for x power n minus 1, you have to do n minus 1 multiplications. So the complexity of evaluating this naively is quadratic in the degree of the polynomial. But this can be done easier if you write this as a1 plus x times, and now you open the bracket, so we can take this x out of the bracket, times a2 plus x times a3, and so on. And then you see there is no more applications of the power function. What we have is n additions and n multiplications, and the complexity is linear. That's the trick, and that's it about the Horner scheme. Okay, yeah. Okay, function approximation versus interpolation. We already discussed this at the beginning. There is this one task which we have, for example, here with the white line. Given the points, we want to hit all the points. That's what we call interpolation. Yeah? And then there is this other task, like here, given a set of points, and here we do not want to hit all the points. We want to have such a fit. Because typically there is the assumption that these oscillations are due to random errors. And we do not want to approximate random errors. We want to approximate some function which is underlying these points. So there is function approximation and interpolation. Interpolation is whenever you know these points are exact and I have to hit all these points. Then we do interpolation. Otherwise, if we know there is some noise which we do not want to approximate, then we do function approximation, which is the different chapter. Okay, but now we continue with interpolation, in particular with spline interpolation. And I already explained to you, given here in this example 4 points, and now we are looking for a cubic spline function. And we will approximate a cubic polynomial between these 2 points, another cubic polynomial between these 2, and another one between these 2. And if this would be all our requirements, our Hiwi would do nonsense again. Because this Hiwi might do something like that. So we could fit a parabola like this, and another one like this, and maybe here a straight line. Yeah. And that's maybe not what we intended. It's perfect. 3 cubic polynomials. So what should be our additional requirements? Excuse me?
It must not be same. Xi will not be same.
It must not be. You mean this polynomial must not be the same like this?
X is different.
What is different?
Solution.
The solution. This one is different from this one, yes. Of course, we get 2 different polynomials, but these guys are not nice, even though they are cubic polynomials. What is your additional requirement to prevent our Hiwi from doing this? This is continuous. This is continuous. Yes.
Maybe the tension should have the same sign in both points.
The tension should have the same sign. Okay. Let's draw a new picture with the tension having the same sign. So let me see. So here we have a negative sign, and I mean this is also a negative sign here. Yeah? Okay?
No, from one point to the next it should be the same, but from 2 different points. So x1.
Oh, I see. Okay.
0 should have the same, and then x1 and x2.
So you say the tension here between these 2 points should be positive all the time.
Yes. Or
But now, how about this picture? You would not. You don't want to have the tension to have the same sign everywhere here. I think that's not such a good idea. Who said continuous? Okay. Yeah, you should go one step further. Continuous is okay, because if the function would not be continuous, that would be bad. I mean, we would have something like that, which is not nice at all. Huh? How about differentiable? I mean, what we had was this. And then here, the function is not differentiable. Huh? Yeah. And that's what we require. We require our function to be 2 times continuously differentiable. Not only once, even twice. Yeah? And now let me show you what that means, that the second derivative is continuous. This is a very strong requirement. It gives very smooth functions. You all know how such a sports stadium with a soccer field looks like. There is this rectangle in the middle, which is the soccer field. And then there is this running track around it. Huh? And it goes, I mean, we have a half circle here and a half circle here. And now this curve here, this curve, the running track, how smooth is it? How often is it continuously differentiable? That's my question to you.
In the soccer field, it is not differentiable. It's a horizontal tangent.
In the soccer field. I mean, we are talking about this yellow line.
The semicircle, excluding the semicircle, it's horizontal tangent.
Excluding the semicircle, which is a straight line here. Yeah?
The tangent is horizontal tangent.
This horizontal line is how often continuously differentiable?
It's not differentiable.
It's infinitely often continuously differentiable. Take the first derivative, it's 0, and the second is 0, and the third is 0, it's perfect. That's infinitely often continuously differentiable. And how about this semicircle? Also. But how about the whole thing? The critical points are these four guys here. How often is it continuously differentiable here? One time, yeah, that's it. And how about the second derivative? Yeah, the second derivative here up to this point is 0. Because the curvature is 0, it's a straight line. For any straight line, the second derivative is 0. How about a circle? In a circle, the second derivative is non-zero everywhere. So that means, I mean, if you would plot the second derivative walking along this line, we would have 0 here, and we would have a jump, and it would be something like that, positive. Okay, so you see the running track on the soccer field or in the sports stadium is only 1 times continuously differentiable. So that might be quite dangerous for these runners running around here. I mean, they're running a straight line, and then immediately they have to jump into the curve. Huh? I mean, yeah, is this possible for humans? It is. But why? Let me tell you why it's possible. Because it does not look like that. This is not the running track. The running track has a finite width. And only because of this reason is it possible. Imagine this would just be a line of width 0. Is there a human who can run on a line of width 0 and get into the curve? No. That's why it's quite wide, about a meter. Huh? Okay, I mean, this is kind of joking. But now let's talk about serious applications of this. A serious applications is railroad tracks. Huh? On railroad tracks, there are curves, bends, and they have to be 2 times continuously differentiable. Because otherwise, if the railroad track would be like that, the train is on the straight line, and such trains are really heavy. And that would mean the front wheels, they would immediately hit this curve, and that would mean a lot of iron due to the friction would be lost and these wheels wouldn't hold very long. And that's why the Krümmungsradius, what is Krümmungsradius in English? The radius, so the radius of this curve is not allowed to make such a jump from, I mean, here we have an infinite radius and here we have a finite radius. That's not allowed. So it has to go smooth into the curve. That's with railroad tracks. And second is on the Autobahn. On the highways, the freeways, if there is an exit on the freeway, I mean, if it would be, so there is the freeway, and here we have the exit. I mean, there is this, it goes out like that. If it would be like that here, then many people, if you're on the Autobahn with 180 kilometers and you enter the exit here, then you would have a serious problem. And that's why they smoothly increase the radius such that you may have a chance to push the brakes. I don't know whether this works with 180. I'm afraid it would not work. Okay, so much about 2 times continuously differentiable. So that's quite smooth. Okay, yeah, and these are our requirements. Given is again a value table with now, be careful, that's important for the following formulas. Now we are given n plus 1 points from 0 to n. Now, and we are looking for such an interpolating spline function s of x with s of xk is equal to yk, so still we have to hit all the points. And s of x must be 2 times continuously differentiable. And now our ansatz is piecewise cubic polynomials. Okay, yeah. Yeah, from this 2 times continuous differentiability, we know that the first derivative of the spline has to be continuous and the second derivative too. And this is a requirement, that's important, this is a requirement for all inner points. And only for these. I mean, what about here? It doesn't make sense to talk about what's on the left of this point. And also, it's not a requirement for these regions here, between the points. Why not? Because we have cubic polynomials. And we know that any polynomial is infinitely often continuously differentiable. So the only critical points are the inner points here. Okay, yeah. Ja.
Das heißt also, der erste Wert, der muss nicht zweimal differenzierbar sein. Haben Sie das verstanden?
So his question is that he said, does this mean that at this point the polynomial does not need to be 2 times continuously differentiable? Huh? Yes, you're right. It actually doesn't make sense to talk about such a margin of an interval, because differentiability of functions is only defined on open intervals. If you have such a closed interval and we are at the margin of the interval, it doesn't make sense to talk about differentiability. Okay? And if it doesn't make sense, we cannot require it. Yeah. Okay. Now let's talk about, we will get a linear system of equations quite soon. Let's talk about the equations we get. No, let's first talk about the unknowns. What are the unknowns? We are talking about polynomials. Here we have 1, 2, 3 polynomials from 4 points. Each one of these 3 cubic polynomials has how many unknowns? How many parameters? 4. Each polynomial has 4 parameters. So here we need to have how many equations? We need to have 12 equations. 12 equations for 12 unknowns. Now we get 1, 2, 3, 4 equations from the points. So 8 equations are missing, or 8 conditions. But now our additional requirements are our function has to be 2 times continuously differentiable. So then we get from, at this inner point, we get one more equation from the first derivative. The first derivative of this polynomial, it has to be the same as the first derivative of this polynomial at this intersecting point. This gives us one equation. The same thing for the second derivative gives us 2 equations. And again, 2 equations from here, which are 4 equations. And now, how many equations do we have? We had already 4. Yeah. So now we have 8 equations for 12 unknowns. Yeah, okay, and we forgot 2 equations. We forgot 2 equations because the 0th order derivative, which is the function itself, this function has to be the same as this function at this intersecting point. And also this function has to be the same as this at this intersecting point. And this gives us 2 additional equations. So we have 10 equations for 12 unknowns. And then there are 2 equations missing. And here we do have a little bit of freedom. We do have a little bit of freedom. We can choose 2 extra equations. You can select whatever you want. But I mean, it's useful to do something reasonable. And what we will do is we will require the second derivative of this first spline at this point to be 0. And the second derivative of the last spline at this point to be 0. Okay, yeah. Now let's go into the math. So we have these points, they are numbered from 0 to n. And now we go only to n plus 1. Look, x0 through x3. But our splines are S0, S1, and S2. So if we have n plus 1 data points, we will get n splines. And that's why this variable goes from 0 to n minus 1. Because we are talking about these subsplines. The subspline Si of x. And now this is our ansatz. Look at this. Ai times x minus xi to the 3rd power. Plus bi second power ci linear and the constant term. You would of course have chosen a different ansatz. You would have chosen Si of x is equal to, what is it? Ai times x power 3 plus bi times x power 2 plus ci x plus di. Why is this over there better? The answer is quite simple. The math is getting easier if we do it like that. And why is the math easier? Look, if we replace for this variable x one of our data points, if we replace x by xi, then everything here gets 0 because we have xi minus xi. Everything gets 0 except the constant term. And that makes the math in the following much easier, and that's why we use this ansatz. But it makes no difference. The result is the same because what we have here is a cubic polynomial. Just the parameters are different from if I would do it like that. But remember, this is our ansatz and not that. Okay, and now we have our requirements. For I equals 0 to n minus 1, we have the requirement the spline has to hit all the points. So Si of xi is equal to yi. This is the requirement, look, that this first spline has to hit this point. And the second spline has to hit this point. And the third spline has to hit this point. Yeah. And now as n minus 1 of xn is equal to yn, this means that the rightmost spline has to hit the last point. And then these are the intersecting conditions between two subsplines. Look, here we have Si and here we have Si plus 1. So one spline and the next to the right. And this means Si of xi plus 1 is equal to Si plus 1 of xi plus 1. And let's look at the picture. This means, for example, that this spline has to hit this point as well as this spline. So these two splines have to be the same in the intersecting point. That's what we have here. And this is the same thing, just we add this prime here. So the same thing has to hold for the first derivative and also for the second derivative. Okay, and that's all. That's all our requirements. And now let's count how many requirements do we have. Here we have n minus 1. And here 2 and here 2. So this is 3 times n minus 1. Plus. This is n. And this is 1. Okay, so plus n plus 1. Oops. So we get 3, this is equal to 3n minus 3 plus n plus 1, which is equal to 4n minus 2. So you see we have 4n minus 2 requirements for how many unknowns? 4n. 4n. Or in other words, 4n minus 2 equations for 4n unknowns. So 2 equations are missing. And that's what I told you before. You can freely add 2 extra requirements. And why are these 2 requirements missing? This is due to the margins. Here on the margin I don't have the condition and here. And now typically we add 2 requirements about these margin points. And the simplest additional requirements, that's what we call the natural spline, is we want to have the second derivative here to be 0 and here to be 0. And look at our sports track. Second derivative 0 means kind of a straight line. So it ends like a straight line. So we don't have, it doesn't end like a curve. This makes sense sometimes, but not always. You can add other boundary conditions. We will look at them. Okay, but now we do this with the natural spline. So we add this condition, the second derivative of our spline at x0 is 0 and at the last point also 0. And now we have 4 n requirements for 4 n unknowns. And this is, of course, necessary in order to have a chance to get a unique solution. The unique solution is not yet guaranteed, but only if we have the same number of equations as unknowns, we have a chance to get a unique solution. Okay, and now what follows is, it's really simple what follows, but it's kind of an ugly computation. And I mean, it would be a good experience for you to read it, but I don't want to dive into it. Yeah? It's simple but ugly, and you can read it if you want, but we don't have to do it here. Yeah? We just start a little bit. Yeah? Should we stop here actually? Yes, we should. Okay, so